The proposed 5-layer nested model for AI design and validation offers a systematic guide for assessing and validating AI applications and workflows. Inspired by XAIQB, it extends to include regulatory and domain perspectives. The model consists of 5 layers: regulation, domain, data, model, and prediction. It addresses AI practitioners' issues daily, aligns with regulations, and promotes fairness, trust, and AI adoption. The authors argue that the technical layer cannot be addressed without regulatory requirements, such as AI transparency. They present 2 preliminary case studies focusing on developing reliable, wise, and trustworthy human-centered AI through ethical and theoretical guidelines. The model integrates explainable AI and human-computer interaction, emphasizing user-centered explainability in AI development. Each layer addresses specific aspects, from regulation to prediction, ensuring AI applications comply with ethical and technical requirements. This innovative approach supports specifying requirements for building AI applications, identifies opportunities for collaboration, and satisfies regulatory requirements, particularly those emphasizing explainability in AI systems. The nested model for AI design and validation is a comprehensive approach to ensure compliance with ethical and technical requirements, promoting transparency, accountability, and trustworthiness in AI systems. It consists of regulation, domain, data, model, and prediction layers that address key aspects such as human agency, diversity, non-discrimination, technical robustness, fairness, and transparency. The regulation layer ensures compliance with AI workflows, addressing potential threats such as inappropriate regulations and operational burdens. The domain layer sets boundaries on processes within the domain's purview, while the data layer summarizes and analyzes data to provide insights. However, potential threats exist at each layer, including inappropriate regulations, no domain oversight, biased data, non-interpretable models, and lack of transparency. The model layer explains the inner workings of the model, including parameters and interpretability, and the prediction layer explains the reason behind predictions and the variables involved. A concrete example is provided, analyzing Google's AI model for detecting retinopathy, which failed due to disparities between training data and real-life data, highlighting the importance of addressing ethical and technical requirements during development. The proposed framework addresses the key requirements of ethical and technical trustworthy AI, providing a comprehensive approach to designing and validating AI systems. By identifying potential threats at each layer and addressing them through appropriate methodologies, accountability can be achieved. This approach conforms to regulatory guidelines, acting as a common intersection between regulatory authorities, ZE, and AI practitioners, and reducing the chances of AI implosion by addressing issues and potential threats with each layer. The research emphasizes the need for a comprehensive regulatory framework to address the unique challenges posed by AI technologies, particularly in the healthcare sector. It highlights the importance of involving domain experts throughout the evaluation process and the use of image augmentation and training data from the same device used in production to mitigate biased training data. The integration of user-centric XAI approaches and collaboration with domain experts is crucial for enhancing the evaluation of AI systems. The study also discusses the significance of open-source models and XAI in enabling transparency in decision-making, as seen in the Zillow Group, Inc. house price forecasting model failure. Furthermore, it presents the feature cloud platform for federated learning as a comprehensive exploration of integrating domain knowledge graphs into deep learning for improved interpretability and explainability. The platform addresses potential threats at each layer of the nested model, validating them accordingly, and considers regulations such as GDPR and European Union requirements for trustworthy AI. The research emphasizes the need for ongoing assessment and adaptation to ensure compliance with legal and regulatory standards. The research paper highlights the growing consensus on high-risk applications of artificial intelligence, AI, and international initiatives working towards harmonization. Key challenges include defining AI, balancing innovation with risk mitigation, and navigating international tensions. Despite these challenges, there is increasing political will for regulation, signs of transatlantic convergence, and the potential influence of EU regulations globally. Potential solutions include establishing global governance institutions, adapting best practices from other high-tech sectors, and developing open-source AI software. The authors introduce a nested model designed to facilitate international harmonization for AI regulations. This model aims to bring together disparate fields of AI and regulation, establishing a common baseline for designing and validating AI under the umbrella of regulation. The research is divided into 4 sections, examining the advantages of AI, the need for AI regulations, the potential of an audience-centric approach to AI, and the development of a nested model for AI design and validation. The XAIQB, a question bank comprising algorithm-informed questions, is presented as a tool to assess and validate AI applications, fostering trust, faithfulness, and transparency. The nested model contains 5 distinct layers: regulations, domain, data, model, and predictions, with specific prototypical questions to be addressed at each level. The paper also discusses the intersection of AI and machine learning in software as a medical device, focusing on regulatory issues and challenges. It emphasizes the importance of explainability in AI systems, particularly in the healthcare domain. The authors discuss the need for transparency and accountability in AI decision-making processes, highlighting the role of human-in-the-loop integration with domain knowledge graphs for explainable federated deep learning. The summary touches on ethical considerations and regulatory frameworks for AI development and evaluation, including the European Union's General Data Protection Regulation, GDPR, and the US FDA's guidance on AI in medical devices. It concludes by emphasizing the importance of multidisciplinary approaches to ensure the safe and trustworthy development of AI systems.